Welcome students. In this lesson we're going to be talking about Newton's third law. Up until now we've talked about the first and second laws, which generally have to do with when the force is acting upon an object. In that sense, it's viewed almost as though the object is acting on its own. Newton's third law has, I suppose, a degree of more real world about it because it talks about forces in pairs. So push-pull happening on forces in pairs. And you may have heard of for every action, there's an equal and opposite reaction. That can be a little bit confusing sometimes. So we're going to reword that as if object A exerts a force on object B, then object B exerts a force equal in magnitude but opposite in direction to object A. So there's some very important parts there, is that the force is equal and opposite, but it's acting on two different objects. So otherwise, if it was acting on the one object, then nothing would in fact move because there would be no forces, unbalanced forces acting. So to use an example here, we've got a little bee flying its way towards a car. Apologies to all the bee enthusiasts out there, but the bee is going to meet a pretty gruesome fate here. So bee is flying its way towards the car. The bee moves towards the car, and then it will hit the car, and we will have a little crash which will take place. And the bee has moved towards the car. In that instance, the force acting on the bee is shown on the left of the screen, and that is 10 newtons, and that's the force of the car acting on the bee. And of course, also at the same time, there is an equal but opposite force from the bee acting on the car, which is on the right of the screen, and that is in the opposite direction. Now, of course, the bee meets a fate worse than the car, and one of the reasons for that is mass comes into play. The car has a much bigger mass, and we know that that's proportional. The acceleration is proportional to force over mass, and so as the mass increases, the acceleration decreases. And so the acceleration of the car is quite small. The acceleration of the bee, unfortunately for the bee, is very large. Okay, so that's an introduction to Newton's third law and an example of that, a real world example. And we're going to focus on when Newton's third law acts on multiple objects. So here's an example where two toy ducks are being pulled along the ground by a happy child. We could talk about why the child is happy pulling ducks along the ground, but let's save that for another day. You have that the front duck is 5 kilograms and the back duck is 2. If the child pulls them with a force of 10 newtons and there's no friction, calculate the acceleration of both ducks and the tension in the string connecting duck 1 and 2. A very common type of problem, which is called a multiple object problem, because in this case there's two ducks, one in the front, one in the back. So how do we go about doing this? Well, actually it's quite systematic. There are a number of different ways you can do it, but I'm just going to focus on one of the ways today. Again, it's always a very good idea to list your assumptions, to list out your assumptions, and they're done at the top of the screen. So we're assuming there's no friction. We are building to a situation where there is friction, but for now we assume there's none. We also assume that the string between the ducks is taut. So this should actually say string. So the string between the ducts is taut, which means that there's no slackness in the string, and it's a level surface. So we have to assume these things. So how do we do it? Well, first of all, we create a single system. So you can see that I'm moving it in here, and we're creating, by the dashed line, we're creating a single system where we have the 2 kilogram duck and the 5 kilogram duck, and we're treating that as one. Why are we treating it as one? Well, one of the reasons is because the string is taut. We are assuming that these ducks are moving at the same acceleration, and so we can treat as one big object. And then we write F-net statements as we always do. So we write F-net equals ma, and we also can rewrite. So our F-net statement is here, F-net equals ma, but also we are writing out the forces acting on this object, on this system. And the main force acting on the system is the 10 newtons applied force. There's no friction. We don't need to worry about friction on the back end because we're saying there is no friction, so we don't need to worry about that, but there is applied force. And so we have a very simple equation of MA is equal to FA, because the F net is only being caused in this instance by the applied force. Now you may say, well, there's definitely tension force in between the objects, but the reality is that this tension force cancels. So the tension force FT1 is equal and opposite to FT2. So FT1 is equal to negative FT2. Okay, so because of Newton's third law, in fact, those tension forces are equal and opposite, and they can be treated as an internal force which doesn't impact the system. Okay, so we have MA is equal to 10 newtons, and then if we isolate for A, it's 10 newtons over M. What's very, very important here is you're treating as one system. So now M becomes 5 kilograms plus 2 kilograms. Which is equal to 10 newtons over 7 kilograms, which is equal to 1.4 meters per second squared. Now we have the acceleration of the system, which is the acceleration of both ducts. We're assuming they're both accelerating with the same magnitude. And if they were not, the strings would not be taut, and it would be much, much harder to solve the problem. So we've answered part A, the acceleration of both ducts. Now in part B, we were asked for the tension in the string connecting duct 1 and duct 2. Well, now we're going to move from talking about it in terms of one big object to breaking it down and talking about one of the objects within our big system. So we've shown that with a green dashed line. We can choose to focus on the back duct or the front duct. My advice on this is choose the one with the least forces acting on it. If you can see, the back duct just has one force, which is force of tension. As an aside, the front duct would have a couple of different forces acting on it. It would have FA this way and FT this way. And of course, FA would be greater than FT, even though the arrow doesn't maybe show that explicitly there. So we're going to not use that because there's two forces acting on it, and we want to just get FT on its own. Well, just choose the object with the least amount of forces acting on it. A lot of times that's actually the one furthest away from the applied force. So create a single system, write F net statements for the single object, and solve for FT. So let's do that again. We know that we've created the FBD for the single object that we're focusing on. We're going to write an F net statement. So again, F net is equal to MA. And it's also equal to all of the forces that are acting on this system. In this case, it's just FT. So now we're solving for FT, and that's what we want to do. So FT is equal to, in this case, the mass of the back duct, which is 2 kilograms. So 2 kilograms multiplied by our acceleration from part A rather, which is 1.4 meters per second squared. Because yes, this is the acceleration on each individual object also. And we get a figure of 2.8 newtons. And because it's moving to the right, I suppose we should really put in the directional component, and we're going to put in R for that. So this is a very specific example of where Newton's third law is being used. You see all of the laws at play here actually. There is a second law because we're using force equal to F net equals MA. Where we see Newton's third law is on the FT forces in between the objects. There's an equal and opposite cancelling force between the objects, and so originally that allowed us to look at this without worrying about them. Okay, so it is important also, what if we added another duct? What would be the situation then? Well, hopefully you guys can actually see that as you add in more ducts, the forces of tension will decrease as you move from the first to the last. So maybe that's something just to play in your mind to make sure that your understanding is good on that. We will do some practice problems tomorrow, and we'll do a practice problem from a multiple object perspective.